All right, let's do a few simple examples to illustrate how to use all these different forces. So, let's say I have a basketball, and I just let the basketball go. We're going to assume that the friction here, air friction, air resistance is negligible. How do we do this problem? Well, first step, draw a picture. We've done that. Next step, make a free body diagram. Step 3, I want to, actually let me make my free body diagram. Assuming there's no air resistance, we have that the force of gravity is just pointing down. That's the only force in our system. We've made our free body diagram. Step 3, we want to sum up all the different forces. Let's do that. I sum up all my forces. I am going to get just the force of gravity. Now remember, we define up as the positive direction, therefore the force of gravity, since it's pointing down, has to be negative, and I know that is equal to minus mg. I'm going to set that equal to the mass times the acceleration. Step 4, we want to solve the algebra. So in this case, let's say I'm solving for the acceleration. I can solve for the acceleration just by dividing through by the mass. And get that the acceleration is minus g, which is minus 9.8 meters per second squared. Here's another example. We want to find the normal force. Almost the same picture I had last time. I have a basketball on the ground. Let's say the ball has a mass of ½ kilogram. We want to find the normal force. Right? So we've already drawn our picture. We've done step 1. Step 2, we want to do our free body diagram. I know gravity pulls down with a force of mg. I know there's got to be a normal force counteracting that gravitational force. That will be my normal force. I've done step 2. I've done my free body diagram. I can see that the ball is not accelerating, therefore these two arrows have to be the same size pointing in opposite directions. I need my normal force to exactly cancel out the gravitational force because I can't have any net force. It's not accelerating. Let's do step 3, which is summing up the net forces. If I add up the forces, I've got a normal force pointing up. I've got a gravitational force pointing down. That has to equal the mass times the acceleration, because whenever I sum up the forces, I always have to get mass times acceleration by Newton's second law. Mass times acceleration. Let's see, I know this is mg. I know my acceleration is 0. So I look at that. I say, all right, I've got 0 on the right-hand side. That gives me the normal force minus mg has got to be 0, which means my normal force has to be equal to the mass times g. Now I can plug in numbers. Since I solved the algebra, I can say this is going to equal the mass, which is 0.5 kilograms, times g, which is 9.8 meters per second squared. 0.5 times 9.8. That will give me 4.9 kilograms meters per second squared, which is the same as 4.9 newtons. Here's another example. Now I'm looking at the basketball mid-bounce. So it's right as it's hitting the floor, The basketball compresses, it smooshes, and the floor pushing up on it causes it to accelerate. So let's say I have an acceleration of 2.2 meters per second squared. We want to find the normal force again. So just get rid of this. We want to find the normal force. I've drawn my picture. Step 2, draw the free body diagram. Even though the basketball is on the ground, it still feels a gravitational force. Whenever you have an object on the surface of the Earth, it's going to feel that gravitational force. We've got a normal force pointing up, except now I need to make my normal force a little bit bigger. Because my basketball is accelerating upwards, so I need this arrow to be bigger than that arrow. The upward force has to be bigger than the downward force if it's accelerating upward. Step 1, draw the picture. Step 2, do the free body diagram. Step 3, let's sum up the forces. Summing the forces, again, normal force minus the gravitational force, which is down, equals the mass times the acceleration. Now my acceleration will not be 0, so I have to deal with that. This is going to be my normal force minus mg equals the mass times the acceleration, because the force of gravity equals mass times g. Looking at this, let's just see if we have enough information to solve. I've got my mass. I know the gravitational field at the surface of the Earth is always 9.8 meters per second squared. Still have my mass. The acceleration I was given, now it's accelerating up. Basketball is accelerating up at 2.2 meters per second squared. The only thing I don't know is my normal force. So I can solve for that normal force. I can say that the normal force is the mass times the acceleration. I can move that mg over to the other side. All I've done is add mg to both sides. The mg over here cancels out. I get plus mg over here. We could do a little bit of factoring here if you want to. You could plug numbers in at this point, but if you want to factor, all we have to do is just factor out that m. So I could say that this is the same thing as m times a plus g. Makes it look a little bit nicer. Which will be 0.5 kilograms times my acceleration, which we said was 2.2 meters per second squared, plus g, which is 9.8 meters per second squared. 2.2 plus 9.8, that'll be 12, times 0.5, so that'll be 6 kilograms meters per second squared, or equivalently 6 newtons pointing up for the normal force. Here's another example. I've got a mass on a spring. In this case, the mass is the same basketball that I've been working with. I want to find how much that spring is going to be compressed, or stretched rather, by gravity pulling the ball down. So I know the spring was originally at some equilibrium length. The ball pulls it down by some amount. It gets displaced by some amount that I will call x. And I want to figure out what that x is. So I know my basketball has a mass of half a kilogram. We're going to say our spring constant is 10 newtons per meter. That's how stiff the spring is. And I want to know how far that x is pulling it down. So I've drawn my picture. The next step is to make a free body diagram. I know gravity pulls the basketball down. I've got a spring that's going to be pulling it up, so I've got to put a spring force in here. I know that the spring force has got to cancel out the gravitational force, so these arrows have to be equal. And the reason I know that is because the basketball is just hanging there. It's not accelerating. So we've done the first 2 steps. We've drawn our picture, we've made our free body diagram, we have a good idea what's going on in the problem. Let's do step 3, which is to sum up the forces. Sum up the forces. I've got a spring force that pulls up. I've got a gravitational force that pulls down. I know that when I add up those forces, I have to get the mass times the acceleration, because Newton's second law says that if I add up the forces, I get mass times acceleration. And I want to plug in the formulas for each of those forces. So let's see. I know that this is mass times the gravitational field. I know that this is negative kx. Plug both of those forces in. Now what I want to do is come down here and say this is minus kx minus mg equals mass times the acceleration. The acceleration I know is 0. So that'll be minus kx minus mg equals 0. Let's see if I have enough information to solve this. I know k, because I was given k is 10 newtons per meter. I want to find x. I know what my mass is, and I know what the gravitational field is. The only thing I'm missing is x, so I can solve for it. Let's see, I'll move the minus mg over to the other side. When I do that by adding plus mg to both sides. Cancels out the mg over here, makes plus mg over here. I can divide through by negative k. Negative k's cancel on that side, but they show up over here, and I'm left with x equals mg divided by negative k, which is the same as 0.5 kilograms times 9.8 meters per second squared divided by k, which is negative k, which is 10 newtons per meter. Continuing with this, 0.5 times 9.8 is 4.9, divided by 10 is 0.49, so this will be x 0.49, or about half of a meter. About half a meter, about this big, is how far my basketball is stretching my spring.